All right, great. So last quarter, I got some complaints that my handwriting is illegible. So this quarter, I'm going to type up notes for all of the sections. So here are the notes for the first one. I'm also building a website slowly. And when it's fully built, you'll be able to see these notes as well as the recordings on the internet. So just be patient with that. Okay. So I guess we're going to begin with an icebreaker. I'll put you into breakout rooms because a lot of the time in my sections, I like to put people into breakout rooms to think about example problems that I'll give you. And it's nice if you know the other people in your breakout room. And even if you don't want to turn your camera on in the big session, please do turn your camera on in the breakout room because it's no fun to be stuck in a breakout room with, with people who don't have their cameras on. Also, someone says they only see code at the address that I sent. Is that true for anyone else? Really? You should. So it's called overleaf. There's something you can sort of slide over and then you can see the compiled version of the code. Is that working for people? Yeah, great. Try refreshing the page if you only see code. Okay, so the icebreakers are listed at the top. What's the best thing you did during your winter break? And what are 2 of your New Year's resolutions? Okay, so I'll put you into your breakout rooms and there are 37 people and I want maybe 4 people in each one. So I'll do about 9. Okay. So go ahead. All right. So I guess I'll go over a few of the rules of section, then we're going to review log rules, and then after all of that, we'll finish the worksheet that you started in class, or we'll try and finish it. It'll be on my web page as well. Someone asked where the recording will be stored. Okay, so some rules of section. I'll try to record the sections and post notes. If you show up but leave your camera off and you don't say anything in the breakout rooms and you don't ask any questions, then I think it's probably better if you just watch the recording because otherwise other people will have to be in breakout rooms with you when you don't say anything and then they might get isolated alone as the only person talking with their camera on in the breakout room. Last quarter, I had one guy show up to office hours shirtless and please don't do that. Don't show up to section or office hours shirtless. No shoes, no shirt, no service. Even though I can't really tell if you're wearing shoes or not, but still it's just like a basic courtesy to wear a shirt. Okay, so also if you'll miss section, you don't have to email me. I don't take attendance, so if you prefer not to go to section or if a different TA's teaching style resonates with you more, that's totally fine. You don't have to let me know. You can just not show up. That's fine. Though I still encourage you to show up. I think it will hopefully help you. And then also, I got a lot of questions last quarter about grades and grading, and I don't really manage that. I have nothing to do with grading or the course materials. And so if you have questions about these things, please either post it on Piazza or if it's a private question, just email the professor. Okay, great. So that's all the administrative stuff for today. So we're going to start on exponential functions and log functions. So question, what's an exponential function? An exponential function is just a function that's of the form ca to the x, okay? So here c is a constant, a is a constant, and x is a variable or indeterminate if you prefer. Some very simple examples are 3 to the x, or 4 times 3 to the x, or 1/2 to the x, and or e to the x. These are all good exponential functions. And exponential functions, when you graph them, they look more or less like this. So if this is 3 to the x, if we want to look at 4 to the x, then 4 to the x is going to end up below 3 to the x here, and then it'll shoot up more quickly than 3 to the x over here. So we also have logarithm functions, or log functions, and log functions are the inverses of the exponential functions. And they have a lot of rules that are very important. One way that you can visualize the graph of a log function is you're just reflecting the graph of an exponential function over the line y equals x. And so log functions, they look more or less like this. And of course, if you take log base 3 of 3 to the x, you just get back x, okay? Great. So let's go over a few of the rules of log functions, which you probably learned in high school, but many people forget them or confuse them. And we'll also try and see why they're true, because I think it's bad to just know something without knowing why it's true. So the first log rule is if you have log base bx plus log base b y, then this is equal to log base b xy. And let's try and prove it. One thing that you could see from the graph of the exponential functions is that exponential functions are one-to-one. So if you have something like a to the x, and you have a to the y, and these two things are equal, this tells you that x is equal to y, okay? And so in order to show that these two things are equal, it's good enough just to raise b to the power of these two things. So we can take b and we can do log bx plus log by is equal to b to the log b xy. That's what we want to show. And let's see why this is true. So we have a plus here, and we know that when we raise some element to the power of something plus something, we can just multiply the respective when you exponentiate b to these two things respectively, we can multiply those. So we get b log bx times b log by. And so this gives you x by definition, and this gives you y by definition. And this thing gives you xy by definition. And so then you get that these two things are equal. So you know that this and this must have been equal. Okay, so if this made sense, can you give me Fs in the chat? So put an F in the chat if this makes sense. Great, great, thanks. Okay, so the second log rule. Oh, you never saw the exponential function like that, or you've never seen Fs in the chat so many times? Oh, okay. Great, great. Well, if you like that, there's more to come. So the second log rule is log x, so log base b x to the y is equal to y log b x, okay? So let's prove this. Again, we can just use the same idea as before, where we use the fact that the exponential function is one-to-one. So we can just do b to the log b x to the y. And this, by definition, is just going to give you x to the y, okay? Because, well, it's definition. And then over here, we exponentiate b y log bx, and we can just flip things around a little bit. So multiplication is commutative, which means that alpha times beta equals beta times alpha. And so what we can do is we can rewrite this as b log bx y. So we're raising this whole thing to the power y. And in this case, the inner thing by definition gives you x, and the outer thing is y. So then you get x to the y. These two things are equal, and so now we've proved the second log rule. Okay, F's in the chat if you're happy. Thanks. Okay, so now we're going to do the third log rule, and then I'm going to see if you actually understand. Don't worry, it's not a graded quiz or anything. So, okay, the third log rule says if we have log base bx, it's equal to log cx over log cb, okay? And so c, this can be any non-zero number that you like, okay? You can choose c to be whatever you want. This is called the change of base formula. So let's see why it's true. We can write b is equal to c log c b, okay, because this is just definition again. And we can write b log bx is equal to c log c. Oh, someone's echoing. Is someone joined on two devices? Maybe everyone mute yourself for the time being so that I don't hear echoing. Thanks. Okay, so we can write this as c log cb, and then this is b, so we have to ask, what can we raise b to in order to get back x? And so the answer here is just, you can raise it to log cx over log cb, and then, oh, nice, these two things cancel out. You get c to the log cx, and this gives you x, okay? And so because this thing is b, and we raised b to the log cx over log cb, log cx over log cb must be equal to log bx, because we can also raise b to the log bx and get back x, okay? F's in the chat if you understand. Also, if you ever have questions, feel free to put them in the chat and I'll try and answer them as quickly as I can. And if I don't see them, just say something. Okay, great. So let's see if you actually understood these log rules. So here's a problem for you. Ignore the one on the document because there's a small mistake. Here, I'll just fix it on the document quickly. It's easy to fix. Okay, there we go. So I want you to tell me, evaluate the following, or write it in a simpler form. 4 to 5 log 99, 100. Okay, yeah, so in your breakout rooms, try and tell me what this is equal to. I'll put you in your breakout rooms. No one.
I'll go for it. Oh shit.
I think I figured it out.
That's good.
So,
Yeah.
do you want me to elaborate?
Sure.
Okay, so I think you can write it on the notation log base b of x equals to log base c of x divided by log c of b, base of b. So in the end, you're gonna have log 3 divided by the first one equals to log 3 divided by log 2 times log 4 divided by log 3, and then you can cancel them out.
Yep. Great.
And so forth.
Thanks. So who said that?
I did.
Oh, thanks. Yeah. So that's exactly right. we have log 3 over log 2. We can just rewrite this, and we'll just use log base 10. It doesn't really matter what we rewrite these things, what base we choose. So we get log 3 over log 2 times log 4 over log 3 times log 5 over log 4, and so on until we get log 100 over log 99. And of course, this term is going to have a log 99 in the numerator. And so we can just do some crazy cancellation, and we're left with log 2 and log 100. So we get log 100 over log 2, and we can just rewrite that as log 2 100. Okay. F's in the chat if you're happy now. Great, great. Okay, so now we're going to go over the worksheet that was given in class. So tell me, did you do the first one in class? Did you finish it? The first problem? The professor told me that I should re-explain it. But if you haven't seen it yet, maybe you should think about it for a couple of minutes on your own first, or in your breakout rooms. Okay, great. Started one, but did not finish. Great. So in case you don't have easy access to the worksheet, it's right here. And why don't you have a quick look at both problems, A and B. I'll give you maybe 6 minutes to look at both problems and discuss them. And it's okay if you don't finish, we'll go over right after you get back, okay? Because if I just go through it and you don't remember what the problems are, then it might be a little hard to follow.
I'm sorry, quick clarifying question. Which worksheet are we talking about? The derivative or exponential functions or the other one?
Oh, so it's the one at the bottom of the lecture, the one on interest.
With the compounds formulas?
Yeah, that's right.
Okay, thank you.
All right, great. So let's go over them. The first problem asks, we decide to open a bank account with an opening deposit of $1,000 and an annual interest rate of 6%. Suppose that the account compounds annually. How much money does the account have T years after it is opened? Okay, so first, what does it mean to compound annually? That means that every year you get paid a bit of interest, and then say that you get paid 6% in the first year. Then you're going to have $1,060. Then in the second year, you're going to get paid interest on not just the 1,000 that you originally put in, but also that $60, okay? So this means that we'll have, in the year T, we'll have 1,000 times 1.06 to the T, okay? Where the 1 represents your original investment, and the 0.06 represents the interest on that investment. So, okay, I think that's all there is to A. Hopefully everyone's happy with that, right? F's in the chat. Yeah, great. So for part B, how many years does it take for Chi Yun to have her money doubled? Good question. So what we can do is we can set this expression equal to 2,000, which means that the money has doubled. But really, I think the moral of this whole worksheet is that exponential functions aren't really about absolute amounts. They're just mainly about ratios. So it'll take the same amount of time to go from 1,000 to 2,000 as from 2,000 to 4,000. So we can cancel these two things out and we get 1.06 to the t is equal to 2. And so then we can just compute in log base 1.06, log base 1.06. And then using the log rule, we can pull t out. So we get t log 1.06. 1.06 is equal to log 1.062. And of course, this part's just 1. So we can get rid of it. And we get t is equal to this expression. And I have no idea what that is. It doesn't really matter. Okay. So now if Qiyun wants to have 15,000 after 5 years, 1,500.
Pardon,
Yeah, go for it.
pardon, I solved the other one in a different way. I was just wondering if it was right.
Sure. Why don't you ask me after class? I'll stick around a little bit.
Okay, perfect. Thank you.
Great. Thanks. Okay. So if Qiyun wants to have 1,500 after 5 years, how much money should she have deposited at the beginning? So, okay, we have 1,500 and our interest rate is 1.06 to the t, and we want some amount to start with 5 years earlier. And here t is equal to 5 because we have 5 years. So what do? We just do division and we get 1,500 divided by 1.06 to the 5. Okay. So for the next one, we're now no longer dealing with annually compounding interest. So let me talk about interest that compounds more than once a year. So in this case, what happens? Say that the account compounds every 4 months. So if the account compounds every 4 months, what this means is that usually after 1 year, you get the full 6% of on your principal for interest. But when you compound every 4 months, instead, what you get is you get 2% after 4 months. So after 4 months, let's see, we start at time 0, say that we have P money. P stands for principal. After 4 months, so this is compound every 4 months. 4 months. And over here, we'll have annual compounding. Okay. And so after 0, we have P for both. After 4 months, we get 1/3 of the interest for the year. So we get 1.02 times P. And here we just still have P. And then after 8 months, we get another 2%, but we get 2% on this instead of 2% on this. So then we get P times 1.02, but then we multiply by 1.02 again. Are we just reviewing? Yes, we are just reviewing worksheet 1. And I'm explaining interest that compounds every 4 months. Okay, great. So then we still have P here, and then after 12 months, we have P times 1.02 cubed, and here we end up with P times 1.06, okay? So could I get F's in the chat if you think that this one is going to give you more money than this one? So we'll call this B and A. Can I get F's in the chat if you think B is greater than A after 1 year? Okay. So this is actually incorrect. A will give you more money than B. And the reason is with B, you're getting paid 6% interest on the principal. The principal is less than 1.02. So what we're talking about is we're talking about the difference between getting paid 3 installments of 0.2. So one way to think about it is, in this case, we're just getting 3 times 0.02. This is, sorry, let me rewrite this. In this case, you're just getting 3 payments of 0.2 in interest, okay, on the principal. But in this case, in the 4-month compounding example, you're getting paid P times 0.2 during the first month. Then you're getting P times 0.2 times 1.02. And we're just talking about the interest here. And then in the 3rd month, you're getting P, or the 3rd cycle, I'm sorry, I shouldn't have said month. But so in the 3rd one, you get P times 0.2 times 1.02 squared, okay? So that's a better deal for you. Does anyone have a question? Some people look a little confused. Okay, I'll just keep going then. So there's also a type of interest called continuously compounding interest. And this basically takes our compounding interest to the greatest extreme, meaning that before we were compounding every 4 months. But if we're continuously compounding, it means we're compounding all the time. And so in the 4-month example, what we're doing is, so you get paid 3 times a year. So let R be your interest rate. So you're getting this much money after each year. So T is number of years. So when we're continuously compounding, it looks like this. So you're getting paid all the time. So 1 plus R over N times N T, and we take a limit as N goes to infinity, okay? And so you'll learn later in this course that this limit is equal to E to the RT, okay? And this comes from the fact that you'll learn, which is this limit is equal to E. Okay, so don't worry too much about that now, but remember that continuously compounding interest, you're raising the rate, or you're raising E to the RT. Okay, so in this case, now we can easily solve the next problem. So we get 1000 times E to the 0.06T, where this is your R and this is your T. Okay, is everyone happy with this? F's in the chat if you're happy. Yeah. For now, you should just know this formula, but hopefully by the end of the course, you'll understand why it's true.
Why is it 0.06 and not 1.06?
Oh, because you're putting in the rate here. It's
I
just,
see, thank you.
yeah, it's just a matter of how this limit evaluates. Okay, great. So for the last part, the last problem, this problem, I think, sort of depends on a population model, which is not given. So there are different population models because when you're growing a population, right, you get to choose how often the population is compounding. But in this case, we're just looking at it on an annual level, which is fine. So in this case, we start with a population of 100,000 in 2015, 100,000 in 1995, and by 2015, we get 200,000. So what's this telling us? this is telling us that the population doubles every 20 years, right? And so what this means is we can multiply the population by a factor of t over 20. And let's see why. Say that p is your population. Then after 20 years, we plug in 20 for t, and we get 2 to the 1 times p, which is equal to 2p. So the population doubles, okay? And so what do we expect the population to be t years after 2015? Well, we just take the population in 2015, which is 200,000, and we multiply it by 2 to the t over 20, okay? And this is your answer. And the idea here is, again, that the absolute numbers don't matter. It's just the ratios of time, basically. So if it increases by a certain fraction over t years, then it'll always increase by that same fraction given t years, okay? So I think that's all I have for today. I'll stick around for a few minutes in case anyone has questions. And my website should be up fairly shortly if you want to watch the recording or see the notes. Thanks for coming to section, and I'll see you next week unless you have questions.
Thank you.
Thank you.